Welcome to The Explainer. Today we are talking about something huge. This invisible engine, really, that's constantly shaping the world all around us.
So, let's start with a bit of a mystery. What's the one invisible force that links something like a super complex silicon chip, a life-saving artificial kidney, and, believe it or not, the very air we breathe?
Well, the answer is this powerful universal process. It's called mass transfer, and it's happening literally everywhere, all the time.
So what is it? Put simply, it's just molecules moving from a crowded place to a less crowded place. That's it. It's a totally natural thing, this tendency to spread out and find balance. And this simple idea, it's the engine behind so much in science, nature, and all the tech we use every day.
Now, I know mass transfer sounds super technical, maybe even a little scary. But you know, the author of the book we're drawing from, Diron Basmajian, he said it perfectly. He said, the time is ripe to approach this topic without a sense of awe. And that's our goal here, to make it totally approachable. Because once you get the basics, it really does unlock a whole new way of looking at the world.
Okay, so let's get into the nitty-gritty. How does this movement actually work? What are the rules of the game?
The core principle, the rule book if you will, is something called Fick's law. Basically, what it says is that the rate of diffusion, how fast things move, is all about the concentration gradient. So think of it this way. The more crowded one area is compared to another, the faster the molecules are going to move to spread out. It's that simple.
You can really think of any mass transfer situation as a kind of tug of war. On one side, you have the driving force, that difference in concentration that's pushing the molecules to move. It's like a packed concert letting out into an empty lobby. But on the other side, you've got resistance, anything that slows that movement down, like, say, a really narrow doorway. And it's this battle, this balance between the push and the bottleneck, that defines almost everything.
And that resistance, man, it can change a lot depending on what the molecules are moving through. I mean, look at this. The numbers show that molecules move roughly 1,000 times faster through gases than they do through liquids. That's why you can smell a pie baking across the house in seconds, but a drop of food coloring takes forever to mix into a glass of water without stirring.
Okay, so now for the really cool part. What happens when we, as humans, learn to take this natural flow and actually harness it? When we start to engineer it?
Let's start with a truly life-saving piece of technology, the artificial kidney.
So, dialysis is basically mass transfer in action. It's brilliant. Your blood, which is full of waste products, flows through a special membrane. On the other side of that membrane is a cleaning fluid, the dialysate, which has zero waste in it. So what happens? You've just created a massive concentration gradient. And boom, Fick's law kicks in. The waste molecules naturally just move out of the blood, cross that membrane, and into the cleaning fluid. The blood gets cleaned, all by harnessing this fundamental principle.
And get this, the scale here is absolutely staggering. The source material points out that the total surface area of all the membranes used for medical stuff, like dialysis, is bigger than the area used in all other industrial applications combined. Let that sink in. This one medical device is arguably one of the biggest, most impactful uses of mass transfer on the entire planet.
Okay, so mass transfer isn't just about medicine. It's also critical for making the high-tech materials that basically power our entire world. A perfect example is the specialized steel they use in electrical transformers.
So how do you actually make this stuff? It's pretty wild. You can't just melt steel and silicon together and hope for the best. Nope, you have to use mass transfer within a solid. They take a sheet of low silicon steel, they heat it way up, and they expose it to silicon gas. And then they wait. The silicon atoms slowly dissolve into the surface and then start to diffuse, bit by bit, deeper into the solid steel, until the whole thing has the exact right silicon content.
And when I say slowly, I'm not kidding. This is the ultimate example of that resistance we talked about earlier. One of the calculations in the source shows that it can take about 16 days for the silicone to work its way just 2 millimeters into the steel. 16 days! It's a powerful reminder that even though the principle is the same, the speed can be completely different depending on the situation.
All right, for our last example, let's zoom out. Mass transfer isn't just something we do. It's fundamental to how the planet itself works, especially when it comes to the environment cleaning itself.
Think about a polluted lake.
How does it get clean? Well, it's a mass transfer problem. The pollutants either evaporate into the air or flow out with the water, but it takes time, a lot of time. Here's a crazy stat from the source. For a lake to reach about 95% of its new, cleaner state, it might need a turnover of 3 times its entire volume of water. 3 times! It just goes to show that nature is playing by the exact same rules, just on a scale that's hard to even imagine.
So, when you step back and look at it all, from inside our own bodies to the vastness of the planet, you see this unseen engine everywhere. Mass transfer is constantly moving, separating, and mixing the very building blocks of our world.
And that leads us to a final, really exciting question. Now that we understand the rules of this game, what are we going to do with them? If we can engineer the movement of molecules, what comes next? What will we separate or create, or maybe even cure? The possibilities are, well, they're pretty much endless.